a question that's very likely to appear on a test would be something along the lines of this. What are the two possibilities that could be true if you have balanced forces acting on an object? Could you answer that question? Raise your hand if you can. Sid?
Either you're at a constant speed or you're not moving at all.
Okay, either you're at a constant speed, because if you're at a constant speed, you're not changing your motion, so you're not accelerating, or you would be at rest. That's another type of not accelerating or what balanced forces could do. All forces cause A, raise your hand. Where at? Okay, I'm more looking, you're right, I'm more looking for acceleration. Okay, all forces cause an acceleration if they're not balanced. Okay, other things, first law. Can anybody quote Newton's first law? It's called the law of inertia, but what is the law of inertia? That's what inertia is. What's the actual law? You're right. Inertia is the object's willingness to resist a change in motion. It's kind of what the law. It's another way of saying what the law is.
Object in motion and motion.
Unless acted on by
An outside force.
outside unbalanced force. Why do I say unbalanced force? If it's balanced, it's not going to change. It's not going to resist it at all. Okay. Then we had Newton's second law. Could we come with what Newton's second law was all about? What was that? Acceleration. Basically the Fermat law, right? The force causes a massive object to accelerate. And we talked about all the things and how force and acceleration were directly proportional. And force and mass were inversely proportional. No, mass and acceleration were inversely proportional. What does directly versus inversely mean?
Same, opposite.
Okay, so directly means the variables do the same thing. Inversely means the variables do the opposite. So, if force and acceleration are directly related, if you increase the force, you're going to increase acceleration. What if you know an object is accelerating less? What would be true about the force? The force is less, because they got to be the same. Okay? What about mass and acceleration? Those should be inverse, which means opposite. This means if you've got a really big object, its acceleration is probably small. Okay? Or if you have a really small object, it's likely that its acceleration is relatively large. And that's kind of the idea of inertia, that objects that are bigger will resist a change in motion more than objects that are smaller. Okay, what else? Lots of stuff. We talked about friction force and normal force. What's friction force?
Contact.
It's a contact force. Okay. What's the other kind of force?
Field force.
Field force. Okay. Then could you list the 4 things that are contact forces and the 3 things? There's a lot of stuff here, guys. We're not even probably about halfway through the chapter.
Rotation. That one.
Well, that's called torque motion.
Shear.
Shear is one. Torque, tension, and
Compression.
torsion. Compression. Okay, how about the field forces? There are 3 of them. Yep, gravitational, electric, and magnetic. Okay. Then we said friction force. There's really 4 types. I'm only wanting you to know 2 of them that are really important. What are they? Static and static is stationary. So the same thing. Kinetic. Kinetic is movement friction. And we said there's a big difference between static or stationary friction and kinetic. What's the main difference? Say that again. Static friction is stronger than kinetic friction. Everyday experience tells us this how?
A box.
A box, okay? It's harder to get it to start moving than to keep it moving, right? Okay. Then we talked about normal. Does normal mean usual in physics?
No.
What does normal mean? There's maybe one of those things that you should be looking through. There's some people that are daydreaming in here as we're reviewing. gonna name names. I just can tell by the look on your face when you're staring off in the la la land.
Perpendicular to the surface.
Perpendicular to the surface. So if the surface is this, you guys know what perpendicular is, right?
Yep.
Okay, 90 degrees. Like that. Okay? So the normal force that the seat is applying on you is straight up on your bootay. Okay? What else? Oh, Newton's third law. What is it? Every action is an equal and opposite reaction. Now, this I remember kind of blew you guys away, that when you walk, it's not that you're pushing the ground, it's that the ground is pushing you that causes you to move. And technically you cause the ground to move, but not very much because the ground is attached to the earth, which is really large. And we know that large objects resist motion, right? Inertia. Okay, resist a change in motion. Okay, I think that kind of big picture hit a lot of stuff. Did I hit every little detail over the past 2 weeks worth of stuff? No, probably not. Okay, but that's definitely the big stuff. So, today, we're talking about free fall. All right, now, not all this stuff do I want you to put in. So just wait before you start putting everything in. You can put the first part in. I want you to write that question in because it's kind of the important question of free fall and one that most people get wrong. And now I haven't defined what free fall is, so that might help. But let's see if you can get this. See what your pre-knowledge would tell me. See how much you guys know about free fall or how little you guys know about free fall. Okay, it says, does a heavier body fall faster than a lighter one? Yes or no?
I want to say yes, but.
You want to say yes, but you're pretty sure it's a no. Okay? So this is a little bit heavier than a piece of paper.
No.
Okay, so a heavier object will fall at the same time as paper, or at the same speed as the paper.
Looks like
So that would suggest that a heavier object falls faster than a lighter object, right? Right? Yeah.
What air resistance have we?
Absolutely. Okay, you're getting into technically free fall. Now, none of us ever exhibit free fall. And here's what is required for free fall. It'll be on your slide later. Free fall is, in order to be in free fall, you cannot have air acting on you. What that means is you gotta suck all the air out and then fall. Have you heard of a vacuum? Not like physics vacuum, not me. Have you ever heard of physics vacuum before? What a vacuum in physics is referring to is something that sucked all the air out of a chamber so that there's no air particles in the chamber. Believe it or not, if I dropped these two objects like this in a chamber with no air, they would hit the ground at the same time. If I dropped a bowling ball and a feather in that same chamber, they would hit the ground at the same time. Let me show you how, let me just give you a pretty good illustration on why it needs to be in a vacuum. Because I just dropped this a second ago, and which one hit the ground way faster? Same piece of paper, right?
Yep.
Pretty much hit the ground at the same time, right? I think I even dropped the pen a little bit sooner than I dropped it. Like virtually at the same time, right? I mean, not all of you can see this, but those of you who are in this room, I mean, within a split second of each other. I could probably drop objects that are quite a bit different in weight, and you can see a lot of the same things. Does that kind of blow your mind a little bit?
Yes.
A little bit, absolutely. So let's. Can we do a vacuum?
Please.
Yeah.
Video.
Yes.
Well, we could create a vacuum, but we wouldn't be able to probably do much more than that, because we wouldn't want to create a vacuum in here. Because if we created a vacuum in here, we'd all die.
Great.
Because if you don't have air, you can't need air to breathe, right? Now, are there, and if you have time, I could probably find a YouTube video of objects being dropped in a vacuum. Because you can create a vacuum. Do it if I have time. Okay. So Aristotle, don't put this in, but Aristotle we know was this great Greek thinker, even though we've kind of debunked that he came up with a lot of stuff that wasn't true. Like when he thought we should study the why before the how, and like when he thought that elements made up earth, air, wind, and fire. Do you remember that?
Yeah.
No, earth, water, fire, and wind, or air. I said air and wind, they're kind of the same thing. Okay. And Galileo, we know, don't put this in, Galileo did a lot of stuff. I'm not going to go into his thought experiment. He basically theorized this idea, and it's actually quite complicated. Take physics, we'll talk about what he did. But in his thought experiment, he said that a piece of paper and a pen would fall at the same exact time. Or not the exact time. They would hit the ground at the same exact time, and that they would accelerate towards the earth at the exact same amount. Okay? Now, do we, in everyday experiences, do we ever experience objects of different masses falling at the same rate? Do we ever experience that? Really? So you've seen something dropped in a vacuum before? Really? Oh. You looked that up? It's nice. Yeah. In outer space, they dropped a hammer and feather at the same time, and they landed on the ground at the same exact time. And why would that work in space? There's a lot of gravity, but there's no air. Okay? So, let's keep going. Let me see what I want. Alright, it says it's not the mass of the pen that makes it fall faster. Because I gave you an example of, again, the piece of paper and the pen, and originally the pen fell faster, right? So it wasn't that the mass changed it because I wadded up the piece of paper, same mass, dropped it, they fell at different rates, correct? Right. Okay? And what Mari said, or what he began alluding to, is that really the important thing here is air resistance. Okay, so you're going to start to see that a bigger component of what we experience every day is more how air resistance affects gravity, more so than how mass would affect how much it gets pulled towards the earth. Let's see, what else do I want? All right, so I want you to put this in. You guys know what rate means, correct? How fast? If you do not know what rate means, you might want to put, I've stated this before, but there are a lot of things that I state that go in one ear and out the other. So if you don't know that, you might want to write that in. How fast an object falls is controlled by the object's weight and the amount of surface area it has. Who can tell me why surface area plays a pretty big role in how fast something will fall? Rose?
That's the surface area, like it will like cause how big of the air resistance you have.
Yep. The more surface area you have, the more area air molecules have to apply a force opposing it. So that's why when I had the piece of paper unwadded, okay, it fell a lot slower than when I watered it up because this has significantly less surface area than if I had it as a flat piece of paper. Only so many air particles are going to hit this as it's falling, versus if it's a great surface area, you have a lot of air molecules that are going to hit it and oppose its motion. And remember, air resistance is a type of what kind of force? Friction force. Yep. So, why is this so important? Well, in your egg drop project, you're probably going to want to create a contraption that
Slows the rate.
might have a high surface area, huh? The higher the surface area, the more it will resist falling, and you want the object to fall slow, right? There are a few other things that we will talk about that go into this as well. What this question is, because I do want you to get the second part of this in. It basically says that will gravity keep an object accelerating forever? Now, the answer to this question depends upon one of two things. Depends on if you are in free fall or if you're not in free fall. And what did I say was the difference between free fall falling and not free fall falling? Air. Nobody hear what I just said? Because we just already talked about how if we have no air, there's no air resistance, and it would continue to accelerate forever. However, if we do have air, eventually it will stop accelerating, and I will explain how. Let's say I drop a baseball. I don't know if that's how you do baseball, but anyway.
Okay.
That baseball has a certain mass, right? Has a certain weight, correct? And what is weight?
The effect gravity has.
So gravity is going to pull this baseball at the same amount no matter where it is, correct?
Yeah.
Okay, so the arrow for gravity on this will be constant. That make sense?
Yeah.
Because it's not going to change its mass anytime soon. Will it?
No.
Okay? Alright. So, the question I'm going to ask you is when I drop an object, does the air resistance stay constant all the way as it's dropping, or does it change? How does it change then? Okay, so if you read it says, the velocity increases, so does the air resistance. What that's saying is the faster you are moving, the more what you have. Now that should make sense, right? Like when you run faster versus walking, you feel the air resistance a little bit more when you're running than when you're walking, correct? Same thing's true if you drop an object from a certain height. Okay? If it's accelerating, it's continually speeding up, correct? So it's getting faster and faster and faster and faster as it falls. Well, if it's getting faster and faster and faster as it falls, the air resistance is going to continue to what? Increase. So let's say maybe at the very beginning, my air resistance looks like that. But then as it gets faster and continues to accelerate, what is that air resistance force going to do? Get bigger. Okay, so maybe after a period of time it's like this. Is it still accelerating?
Yeah.
Why? How do you know it's still accelerating? Everyone should answer this. It's an unbalanced force. Okay? But then it gets faster and faster and faster. Air resistance continues to get bigger, continues to get bigger until the air resistance completely balances out the gravitational force. Now you have balanced forces, and if you have balanced forces, what is always true? Or you're not accelerating, and so therefore you're going at a constant speed. Everybody hear that? So it was accelerating all the way to the point where it was moving so fast that the air resistance completely balanced out the gravity. So if you're not accelerating anymore, is the object you drop going to get faster at any more than that point? No. That is called your terminal velocity. So put this in. Yes. No. When I say when the air resistance is enough to balance out gravity, it's still moving really fast. It's just not accelerating anymore. It's not speeding up anymore. Does that make sense? You with us, Maura? Okay. So what's free fall?
Falling without air resistance.
When an object's falling with no air resistance. Does this ever happen in everyday experiences for us?
No.
No. Okay? When we fall, or when we see these things fall, usually it's with what? Air resistance. Yep. Okay? And we said that air resistance, as you get faster, or as the object moves faster, the air resistance gets greater. Okay? Now, if we were in free fall, meaning no air resistance, would the object ever reach a speed where it was at its maximum? No, technically not. So if you could drop it from an infinite height in a vacuum, it would speed up forever. But we know that first off, we don't have an infinite height. Second off, we don't have an infinite vacuum. Okay, so that's just in theory, guys. But if we drop an object in real life, eventually it will reach its terminal velocity, which as an object falls, it gets faster and faster, which does what to the air resistance? It increases. Eventually, it will be moving so fast that the air resistance will what? Balance out the gravitational force. And at that point, can the object get any faster?
No.
No. Okay, so it accelerates all the way up to that point. As soon as you get the balanced forces, it will just continue to fall at constant speed. Are we starting to see some of the stuff we talked about at the beginning of the chapter?
Yeah.
Starting to play out here now in the middle of the chapter?
Okay.
So, this is your definition of free fall. But I might also add, because it says when an object falls with only gravity acting on it, that means no air resistance, correct? So if you want to write that in underneath it. So this is your definition of free fall. And normally, unless you have created a vacuum or you're in outer space, which neither of these things we've probably ever naturally experienced, okay, this is why probably the idea of free fall doesn't always make sense right away, because we never see it. Experience tells us that a big object, what? Falls faster. But the real thing is, it's not that it falls faster, it's just it has less air resistance. So this is going to be a pretty big thing you're going to want to know. So star it, underline it, highlight it. You got to be able to know what free fall is, and obviously what the effects of that will be. Got it? Woo! Oh, I was spilling a lot of water all over my stuff again. That was a bad day. That was a bad day. Those of you 8th period movers never got to experience that awful day. I was just having a talk and I just knocked my water all over everything. I had to, yeah. Let me see. Okay. All right, I do want you to put this in, but before you put this in, let me do a quick explanation of this. Okay, I don't want you to be putting it in because you're not probably listening to me if you're putting it in. This is a free fall cannot happen if an object is in the atmosphere. Why is that? Because atmosphere means air. And air means that you're going to have air resistance. And another word for air resistance is drag force. Okay, secondly, it says if an object falls in a vacuum, which means what? No air, then there is no such thing as terminal velocity, which means it will accelerate forever. Put this in. Or until it hits, the ground. But. Okay. Free fall means no air resistance, means you're never going to reach a terminal velocity, you're always going to accelerate. But everyday experience tells us that we are not in free fall because we never fall without the air. And if air is involved, you have air resistance. And you can reach your terminal velocity. So I already explained this. As soon as we're done, we'll move to the next slide. Hopefully we can get enough time at the end of class where we can look up a YouTube video. As you're writing this stuff in, are you reading it? Are you comprehending it? Are you thinking about it?
Yeah.
Are you mulling it over in your brain? Because if you just idly write it, you're losing a really, really important study tactic. Okay? But if you mindlessly write it in, you're losing that advantage. All right, so gravity and its effect on weight. Almost done here. Now we've talked about weight, right? Weight depends on gravity. So if we could change gravitational force, we could probably change the weight. Let me see here. Kind of a lot, but I'd like you to have it so that when you do look through your notes and study 10 minutes a day, like you're supposed to, you'll be able to come across this and it'll bring back what weight is and how you should be able to determine it. Now, it says A there is 9.8. That is the acceleration that all objects experience due to gravity, whether the object's big or small. What that simply says is a bowling ball and a feather both accelerate towards the ground at the same acceleration. The only difference is the feather's going to have more air resistance than the bowling ball will. So, what you could do is you could go home, you could step on your scale, you could find your weight. How would you do that? Oh, I kind of gave that away, didn't I? By stepping on the scale. Okay, by stepping on the scale. And if you know that you get accelerated by gravity this much, could you figure out exactly how much mass you had? So for example, let's say I weigh, I don't know, this is just a made up number. Holy, can you even see that?
Yes.
300 newtons, that's my weight. Okay? You're probably thinking that's a lot, it's actually probably less than what I weigh. A newton, I think, is equivalent to 1 pound, or 5 newtons is 1 pound. So yeah, that weighs less than me. Well, yeah, that was a lot less than me. Okay, so if we have our mass and we know gravitational pulls every object at 9.8 meters per second squared, could I figure out the mass of myself? Could I figure out the mass of you guys? If you guys stepped on the scale and figured out what your weight was or your force due to gravity, you can figure out exactly how much matter is in your little bodies. Cool, huh? Now, next slide. Do not put this in. This is just a reminder that this is from way back in chapter 3 when we talked about.
Attention high school students. If you are going on the anatomy field trip on Friday, please go to Mr. Stafford's room after lunch today. If you are going on the field trip for anatomy class on Friday, please go to Mr. Stafford's room after lunch today.
Okay, so mass is the unit of measurement that measures the amount of matter you have. You do not have to put this in, this is just quick review. You can only measure mass either by using a scale that compares one mass to another, or you can find your weight and use the equation. Weight is a force and must be measured by a scale. Now, mass never what?
Changes.
Okay, when I say this, can our mass change? Yes, because every day we're ingesting food and our body is burning down food. So yes, our mass will change, but will that golf ball's mass change?
No.
Will this chair's mass change? Will you name its mass change? No, okay? But weight can change. Why? Because it depends on how much gravity you have. If you're in outer space, you don't weigh very much. If you go up into Colorado, you weigh a little bit less. Okay? So, when I say that things accelerate due to gravity at 9.8 meters per second squared, that's true if you're at sea level. If you're in Colorado, it's a little bit less. Is it a lot less? No, but it is a little bit less. If you go up on a mountain, you're going to have less gravitational attraction. And we know this because you're further from the center of the Earth. And we said distance affects gravity. The further you are away, the less gravity you have. Alright, so you don't have to put this in because, didn't I have you do this equation when we talked about weight earlier this chapter?
Yes, sir.
That looks familiar?
Yes, it
Really?
does.
And I told you that little g was 920, did I tell you that?
Yeah.
Are you sure?
Yep.
I don't remember telling you that.
Well, you did.
Because the yeah, I don't think
Hold on, don't leave yet. I want to check one thing here. Here's what I want you to put in. Before you leave, I'm pretty sure I showed you this equation. I swear I did.
You did. I was here.
I
I
Why?
saw
You
you.
think I did too? Okay.
there was.
But I don't remember telling you what
Yeah, you
little
did.
g was.
You did.
No,
I did?
Well,
I had to if I gave you that equation.
proportionality constant.
Oh, did it say 921?
No, it just says proportionality constant. Oh, wait, yeah, there's proportionality constant.
Oh, yep. Okay, so you do have this in your notes, and I'm not going to make you rewrite it. Okay, it is in your notes. You're welcome to rewrite it if you want. I know. I did. Worst red marker. Off the heat.
On the PlayStation? Not a computer, because your computer's way down there. Oh, the phone and the phone and the.